It's a great honor and pleasure to introduce the second speaker of this morning, Dr. Cyprien Delpech de Guilhem. And Cyprien will give you an update on computing on encrypted data.
Thank you, Bart. Hello, everyone. So today I'm going to be introducing the topic of computing on encrypted data. And it's going to be a bit of a mix of different kind of cryptography technologies that you are seeing in this course. But I'm going to try and present them under the sort of common umbrella of trying to compute on encrypted data. So we're going to start off with a bit of a problem statement, and then we're going to go through different technologies that have been proposed in the past, so a bit of a historical perspective, sort of, about different ways that you can realize the sort of abstract goal of computing on encrypted data. And if I have time, I'll be talking a bit about overviews of use cases, but if I don't have time, the slides will be available afterwards, and the examples are kind of fairly self-explanatory once you've seen kind of the first two parts of the presentation. So data encryption is arguably one of the core goals of cryptography as a discipline. And you can kind of divide it into three categories. So there's data at rest, which is, well, you know, when it's not arguably the original, because, you know, when Caesar was trying to send messages to his general, you can call that data in transit. But it's kind of the simplest model is to look at data at rest. So you want to encrypt your data, store it somewhere so that no one can stumble across it and then pick it up and look at it, and you want to come and pick it up later. So this could be hard drive encryption, it could be device encryption for your mobile phone. All of these, or you want to store, you know, an encrypted database in the cloud and like retrieve it afterwards. And this is all arguably solved with symmetric key encryption. So you need very clever symmetric key encryption in some cases, but that's most of the time sufficient. Data in transit, well, you move from one person to at least two, right? So you need something a bit more complicated, and this is where public key encryption plays a role. So you've, I think, heard a bit about TLS. Most of you know like the Signal, kind of end-to-end encryption, WhatsApp, Facebook Messenger. These are all kind of derivatives of the initial concept of public key encryption, and it helps to secure data in transit. So with those two things, you can store your data somewhere safely. You can send your data to someone safely. But then there is the question of how do you use data safely? Because with both of those things, at the beginning, none of the the schemes that we know. So if I tell to the server, here's my encrypted database, please compute something on it, the server's going to be like, what do I do with this? It's just random bytes, or at least random looking. I can't do any kind of meaningful computation with it. So right now, most of the time, what you have to do is you have to allow the server to decrypt the data, or just give it in the clear, and request computation on this. And so, arguably, you don't want to do that, because then the server who's doing your computation can see everything. So, I also introduced these things as kind of like, okay, number one, there's only one party involved, and that's the data owner, and they're the only one who need to manage any kind of cryptography. They can put the encrypted data somewhere, but then that doesn't really matter. In the second case, we've got two people, probably a sender and a receiver, but they're both kind of interested in maintaining the privacy of the computation, of the communication. In the third case, there's sort of more questions that arise, because once you're computing with data, especially in today's world where, you know, you have like internet users that are sort of data sources, and then you've got companies that collect them, and then they can be sort of data providers. So that's kind of the first question. Whose data are we talking about? Whose data are we aiming to protect during the computation? There is the second question of who is it going to be used by, in the sense of like who is computing on the data? Are they the same people as the ones who hold it, or are they different? You know, what kind of computing powers do they have? Are they significantly more resourceful or not? what kind of oversight, what can we trust them to do or not to do, these kind of questions. And then the third question is used for whom? So once you've actually processed your data, well, it might not be the original data owner who's interested in the result, right? Like the person who managed to compute something useful, they might want to monetize that. So for example, you can have a machine learning company as number 2 interested in training a machine learning model on a data set from people in number 1, but then actually making this model available to other people as number 3. So this could be like a medical application, for example. Patient data needs to be used to train a model. Someone needs to do the actual training, and that might not be the hospital or the collection of hospitals that owns the data. And then medical researchers or diagnosticians would want to use the output. So these are kind of, when you're considering the sort of application of computing on encrypted data, these are kind of some of the key questions you need to remember. It's not just what kind of cryptography, what kind of computing technology should I use. It's more, well, it is about that, because as we're gonna see as I talk about the technologies, some of them they all have advantages and disadvantages, so you'll want to pick the technology that fits the use case, but you also need to pick the technology whose trust assumption fits the use case, about like the configuration of who owns what, who can be trusted, and so on. So these are kind of like, they're a bit more sort of privacy related than cryptography related in the sense, but they're important to keep in mind. So with this, we're gonna start looking at possible different methods for computing on encrypted data, with originally the goal of preserving input privacy, right? So the first kind of goal of encrypted data, the main one, is we're gonna have some inputs into the data and we want to protect their privacy. We want the people who are computing or obtaining the output not to be able to learn specifics about the inputs. There's other considerations that we'll come to afterwards. The most naive way of doing computing on encrypted data is to not encrypt the data. You just send it, you let whoever is doing computing compute it in the clear. And here the only thing you have, I'm not saying this is insecure, technologically it is, but legally sort of it isn't, because you're making trust assumptions on your computing platform, for example. You probably enter some kind of legal agreement with the computing provider, especially if you don't just use a cloud instance, but you actually set up some kind of contract or something. And then you've got legal remedies, right? You can say, hey, if you breach my privacy, if you breach my security, I'm gonna sue you. And for a lot of companies, that's a threat. So if they have a threat not to do something, they'll probably not, well, they're less likely to do it. So, but that's the only thing you have, and it's long, and it's expensive. And the thing is, this is only after the fact remedies. So they can breach your security, they can breach your privacy, and the only thing you can do is punish them for it, but you can't take it back. They've already gotten away with the breach. So obviously we want to do better than this. Another method that's been proposed is using trusted execution environments, which is also called confidential computing. And here the idea is that there is a sort of a secure hardware enclave on the hardware that is provided by like a service provider. And in the idealization of this thing, this secure enclave is a black box to the server that is executing it. So the server provides power and cooling and sort of data paths in and out of this secure enclave, but it has no idea of what's happening on the inside. And so what you can do is you can encrypt the data before, send it encrypted into this enclave, and then decryption happens within the enclave, processing happens on clear text data, so in the plain text domain, but it's re-encrypted before it leaves the enclave again, and then the encrypted traffic is sent back to the output party. So in the ideal model, that kind of works because you have kind of this secure enclave that the cloud owner cannot look into, but for, and here I'm not a hardware researcher, so I'm going to qualify, but for almost every such proposal, there has been academic evidence that mounting what's called side channel attacks is possible. So if you actually execute the piece of hardware, if you actually have the piece of hardware executing computation, you can listen to it, sort of electromagnetic radiations, power consumptions, these kind of things. You can listen at what you can see, and you can sort of reveal some of what's happening inside. And to the point where you can extract meaningful information about the computation that is happening and about the inputs that are being used. Because at the end of the day, computation happens on plain text bits in the hardware. So you can extract some meaning. So while there is academic evidence that it is possible, there is no publicly available evidence that it has happened in cloud providers that advertised trusted execution environments as a service. But this already raises kind of a lot of trust assumption questions, right? If you're not going to trust them with your data in the first place, why would you trust them not to use these side channels that are available to them to try and look at your data? So it's not a very satisfactory solution from the perspective of, no, I really want to achieve input privacy for my computation. So this was kind of like a hardware-based solution. Then there is the method of what's called federated computation, which is a bit more of a statistical approach. And here the idea is that when you have a computation that you're going to try and do, in this example, for example, we have three sort of data holders. They all have a database, and they want to compute the average age, let's say, of the people in their database. So this is a computation that happens to split mathematically, in a way that each data holder can perform part of the computation themselves. So they can compute their local average, for example. And then they only have to share with each other this average. So X, Y, and Z are the averages of the ages in the databases. And then you can compute the global average by performing more computation. So in some sense, what you're doing is you're sort of anonymizing-ish the people in the individual data sets by already computing on their aggregated data. And because it's the data holder that does this themselves, there's no privacy issue. And the only thing they're revealing is this kind of aggregated average so that the computation can continue. So here the example is about averages, but it's always possible to try and sort of split more complicated computations into a similar sort of local phase and then global phase. But it's always a bit tricky, and this is also very application dependent. Not all computation will be amenable to being separated into a local phase and then a shared phase. And then there is the additional question that, while you are revealing information in this case, we're not talking about adding any kind of privacy measures to the local output, the local averages. So as a one-shot thing, it looks okay. You're saying, okay, well, the local averages are hiding the people, but then you have to consider what happens when this is placed into part of a bigger system. So let's say this is like a query response system where there is a person at a terminal who can make queries and say, okay, I want the averages of the ages, and then I want the averages of the age of the male people in the database, and then I want the average of the age of the male people who are like over 30. So you can start crafting queries, and because you're querying the same database each time, you can eventually craft things that that can lead to situations like this. So you've got a group, you can manage to craft a query which concerns 51 people, and then the next query concerns 50 of the same 51 people. So if you have the average for 51 people, and then the average of the same thing for all of them but one, then mathematically you can actually extract the individual value of the person that you excluded from the second set. So this is what's called an active attack, and especially like an adaptive attack, because it requires the adversary to make adaptive queries based on previous ones. So it's like, it's a stronger security model to consider, but it's also more realistic, right? Most systems we want to deploy in the world have this kind of input-output response, this interaction with its users. And so you can always, it's better to assume that the adversary can try and cleverly craft their requests based on their past requests. And it's what also we call a differential attack, because you're exploiting a difference between results. So this is where the other sort of method of differential privacy comes into play, and I think you've heard a bit about it yesterday already. And here the idea is that we're going to add some noise. We're going to add some noise, for example, at this stage. So when you compute the local average, you can publish that with a little bit of noise, and similarly for the other ones, so that when you do the averaged out computation, you end up with some noise in the result. The idea of the noise is that if you make your data set noisy, or the result of your computation noisy, you're actually blurring sort of your data set. And so when people try to extract information, statistically it can be shown that they don't really get meaningful information about the original data, because the noise is high enough to disturb this. And it provides some measure of privacy. The flip side of this is if you add too much noise, you're going to flood your output, and then the computation is no longer going to be meaningful. So here you also require analysis, but in the kind of the other direction, to make sure that you're not adding too much noise so that your computation loses value. So here you have a kind of what we would call a Goldilocks dilemma, where you just need the right amount of noise. And that can be tricky to figure out what it is. And it can be tricky to add in the right places in the computation, right? You need to carefully analyze how the actual computation is going to be represented and executed so that the noise is just right. So we've seen a bit of a hardware method. This is a bit more of a statistical method for ensuring kind of privacy while computing on data. And then we can now move on to the more really cryptographic and sort of mathematical solutions. So the first is what's called homomorphic encryption. I suppose that's a term a lot of people have heard already. Encryption implies that you've got sort of a plain text domain that your data sits in the clear, and you've got a ciphertext domain where your data is encrypted, and if you don't have the secret key, it's hard to go from the ciphertext domain back into the plaintext domain. The thing about homomorphic, so maybe for the non-mathematicians out here who haven't heard this term, homo is same and morphem is shape. So that means that essentially your plaintext domain and your ciphertext domain have the same shape in some kind. And that means it's meaningful to do something like this. Addition in the plaintext domain is meaningful. You can add two numbers and get a meaningful number out of them. And there is a meaning associated with adding ciphertext to each other. And that's not something that's very common in encryption normally. So not only is there meaning to adding ciphertexts together, they also have the property when you do addition in the ciphertext domain, it translates to under the hood addition in the plaintext domain at the same time. So if you have a scheme that has this property, then you can see you can do, well, with this you can do linear computation. If you can encrypt your data like this, you can perform linear operations on all of the ciphertexts, and this will perform the matching linear operations on the plaintext without requiring any knowledge of the secret key or of the plaintext value. So if, let's say we have this, then we need to think about, okay, what's going to be the data holder structure that this technology is going to work in? So encryption works with a key, which always means there is someone who is capable to decrypt. The person who can do these operations doesn't need to know that key for this. So the important thing about homomorphic encryption is that the person who generates the key cannot be the same as the person who is going to perform the computation. Because the person who is going to perform the computation is going to be given all of the encrypted inputs so that they can perform the homomorphic computation. But so if they are also the key holder, well, why bother with doing homomorphic computation? They just decrypt the inputs, do the computation in the clear. That's much cheaper, and it's also not secure because now they've just decrypted the inputs. So the person who actually needs to generate the key pair needs to be the person who wants the output of the computation. Because that's the only phase of the computation when you require decryption. They can be one of the data holders, that's not an issue. They just cannot be the same as the person who's going to compute. So then once you have a key pair generated for the encryption scheme, you can give out the public key to the data holders, just like any normal public key encryption scheme. Then they can encrypt their inputs under this key, and then they can give it to another party, which could maybe be one of them, for example, or not. It could be a cloud provider, something like this. And then they can compute the computation that you want in the ciphertext domain. And by the homomorphic property of the scheme, you have the matching computation in the plaintext domain, and then they can return the an encrypted result, which could be the final output, or it could be like an intermediary output in the computation. You can say, okay, we've reached sort of enough, we're literally just going to send a partial result, and then the output party can decrypt it, and then maybe perform further computation on the decrypted results. So in this case, we have a linearly homomorphic encryption scheme, so division by 3, like division doesn't make sense in the ciphertext domain, because the only thing we can do is add or subtract, but we can't divide. So in this example, we have to stop after we finish the linear part of the computation, and then decrypt and continue in the plaintext domain with the nonlinear part of the computation. So that means you can't do general computation with this, but it's not the end of the world, because there are many things you can do with linear functions. So like you can compute averages, there are some statistical functions you can do this. There's encryption, there's like sort of electronic voting schemes that use additively homomorphic encryption, where voters encrypt their votes, and then you can add all of the votes for a specific candidate, and then only decrypt the end result. So then every vote is encrypted and never decrypted on its own, and only the total of the votes is revealed. So that's an example of homomorphic encryption, where you're preserving the privacy of the inputs. But if you want to do general computation always on encrypted data, you need nonlinear function, and here you need what's called fully homomorphic encryption, and this is where the acronym FHE comes from, where it makes sense to add in the ciphertext domain, but it also makes sense to multiply in the ciphertext domain. So having this kind of second binary operation that's available to you is what enables general computation, and of course it has to it has to have the equivalent effect on the plaintext domain. But this is something that's much more complicated to achieve with the same encryption scheme. So we have schemes that do addition, we have other schemes that do multiplication, but it was quite challenging to come up with schemes that do both. The first proposal for this was only it's 15 years ago, which in cryptography is a fairly long time, but in technology is and also isn't. So we're just about getting to the point in the last sort of 3 to 4 years where these original schemes have been optimized and improved enough to become practical to some extent. So there are some things where it's fine to do FHE with, there are other things where it's not fine yet. But in all cases, this is kind of the key point of FHE for input privacy. It's the decryptor, so the holder of the secret key, has to be different from the party who's computing, because otherwise using a homomorphic encryption doesn't actually give you additional input privacy. So now we look a little bit more about, okay, well, like I said, how practical is this? The thing with homomorphic encryption is that it provides usually quite large ciphertexts for the plain text that it is able to encrypt and operate over. And the homomorphic, like the fully homomorphic encryption schemes that we know of are based on like the lattice problems that Professor Verkautelen talked about just before. So there is this concept of noise, right? Lattice-based encryption is noisy, and you need to like move, if you have a bit, you need to make sure you place the 0 or the 1 far enough from each other in the plaintext domain so that you can still tell which was which after you decrypt. Well, if you have noise on one ciphertext and noise in another, and then you add them in some way, that noise is going to grow a little bit. And if you multiply them, it's going to grow even more than when it grows when you do addition. So the only way we know how to do fully homomorphic encryption is with noisy encryption, and this noise grows the more computation you do. And at some point, the noise would grow so much that it erases the plaintext data in some sense. So there is a limit, depending on your parameters, depending on the FHE scheme that you chose, there is a limit, and this is why we talk about low multiplicative depth circuits as being usually fine for homomorphic encryption. Because as long as you're not doing too many multiplications, your noise growth is controllable, and that's fine. There is a technology called bootstrapping, which essentially means you can encrypt your encrypted ciphertext and then internally decrypt it to kind of remove this noise under a layer of encryption. So you're doing homomorphic execution of the decryption operation to remove the noise from your ciphertext, and then hopefully what comes out of this is the same plaintext as before, but with less noise. So if you've managed to do this, then you can just, whenever your noise goes too big, and when you set parameters, you kind of know I can do 100 multiplications and then that's my limit. You do one of these bootstrapping operations and then you've got 50 more multiplications you can do. So you do 50 more, bootstrap again, you can do 50 more. And the problem is that these bootstrapping operations are expensive and they take time. And so when you have very high depth circuits, that becomes a huge bottleneck. So you can do things like decision trees, you can do inference, machine learning model inference is fairly low depth. You can sort of approximate maybe activation functions as well. So this is like a conceivable result, but it's really depend on how much data, the actual algorithm you're going to use, and these kind of things. Training not only usually requires a very high depth algorithm, which is difficult to do efficiently with FHE, but the other thing about training in machine learning is the recursive and iterative nature of the training. When you train a machine learning model, you give it a training data set, so you know what the data should be categorized as. You run your untrained model on it, it makes a lot of mistakes, and based on how good or bad it predicted, you punish or reward. And then you do your algorithm backwards to kind of take those rewards and propagate them into the model. And then you repeat that back and forth until the error at the end is not so big anymore. The thing is, if your data is entirely encrypted, how do you know when your error is not so big anymore? Because it's all in the plaintext domain, but the only thing you're seeing is ciphertext domain stuff. So you can't actually test how good is my data, how good is my error. So you're left with not knowing when to stop this iteration because it kind of depends on the inputs that you want to keep private. So that's one of the challenges of secure computation, whether with homomorphic encryption or other technologies, is when you've got like conditions that depend on private inputs. You need to handle that in a way that doesn't leak the input data. So if you have a circuit that branches with like a really expensive branch if you have a 0 value, but like a really short branch if you have a 1 value, well, if you can tell that your encrypted operation is taking the short branch, you know which value it was. So these are the kind of also considerations around computing on encrypted data that it's not really the job of the homomorphic scheme exactly to deal with this. It's like an added layer of like secure programming in some sense. So the other technology for securing inputs is secure multi-party computation. Its goal is the same as FHE, which is to execute arbitrary computation while preserving the inputs of the parties. But rather than using homomorphic, like sort of public key cryptography to do this, it uses interaction. So while interaction can seem a bit like, okay, you're just talking to other people, in cryptography, in computer science, and in complexity theory, the set of things you can do when you have an interactive channel is greater than the things you can do when you're on your own. And so the security from MPC computation actually comes from the fact you have several parties. So that means you need to move from a model where you have a single computing party, which could be a cloud provider, to multiple computing parties, sorry. So then that trickles down to your trust assumptions and to the business model for your application. Also, you need to say, okay, we need to have multiple parties that are all interested in doing this in doing some computation. And the thing is that in MPC, the security is always if some set of parties collude, you might lose security. So you can say we have an MPC protocol that is secure when all but one parties collude. That's like the best case scenario, because obviously if everybody colludes, then they can just do whatever with the inputs. But if you say, okay, I only trust no more than half of them to collude, so you have an honest majority of parties, you can have a much more efficient protocol. That's what research says. So, you know, are you willing to trust that no more than half of them will collude with each other so that you can have a faster application? Or do you really not trust that and you say, I will only trust that one of them will remain honest, and then, well, you have to use a more expensive protocol. One of the things is if you are yourself a data holder and also one of the computing parties, then you can just say, I trust myself not to kind of collude with anyone else. So in this sense, you can be part of the computation and guarantee this, which is something you can't do in FHE, right? Like there is only one person computing, and usually if you're encrypting your data to delegate the encrypted computation, it's because you don't have the computational resources to do the computation yourself. So that's why you outsource it. The thing, on the technical side, MPC doesn't work with what you could call encryption. It works with a more information theoretic thing called secret sharing. So this idea is that every data element X is there is a way to share it across the different parties who are going to participate in the computation. So in this case, this is like an additive sharing. So you can just create the secret back by adding the different shares with each other, but there's different ways to do this. When the trust assumptions on the colluding parties change, right? So if you have something like this, each share is supposed to look completely random. So if I'm given one share, it just looks like a random value. I can't make sense of it. And even if I have two of them, the third one is still random. So this is a secret sharing that means if you know all of the shares except for one, you still have no meaningful information about the original secret behind them. And you really need all shares in order to recreate the secret. It also means that if someone decides to lie on what their share is, they can influence what the reconstruction is going to provide as an output. So this is secure against colluding parties that try to extract information, but this is less secure against people who are trying to influence the output of the communication. But this on its own. There are other mechanisms that prevents this. But in this case, for example, this is an example of linear secret sharing scheme, right? So again, the kind of homomorphism property. And because here this is completely linear, computing linear functions is then trivial. So the person has the data, shares the data, and then each party can just do the linear computation on all of their shares of the different inputs. and that will produce a share of the output of the computation. So it's kind of like there's the share domain and the secret domain, and if you do linear computation in the share domain, it does the same computation on the secret domain, and then at the end you just need to reconstruct. However, nonlinear operations don't work like that, because for example, let's say we have x like this and we have y also shared like this, then x times y is going to have cross products between the shares, right? You're going to have x1 times x2, x2 times x3, and so on. And so the parties can't just send those shares to each other to compute these cross products, because at this point they're revealing the input x and y. So you need a different way to do this, which does require interaction between the parties. So you blind your inputs, you perform multiplication on the blinded values, and then you remove the blinding afterwards. And then you get shares of the product. But you need to exchange information. So the way the workflow would kind of work, and then you would repeat this across all three parties, but here you have party 1 with their secret X, they create 3 shares, they give those shares over secure channel, and this, we know how to do secure data in transit, so this we can do. And then they all have shares of the inputs. Whenever there's a nonlinear operation in the computation, they exchange with each other. And then at the end, they all have a share of the output, and you can just reconstruct. So as I said, this is nice, it works. Secret sharing is fairly inexpensive, right? So if you want to share, let's say like a 128-bit integer, you would use shares that have about the size of 128 bits. So you don't actually have a blow up in the size of the data that you would have with homomorphic encryption, where you need to go from plaintext domain into the ciphertext domain, and elements in the ciphertext domain are much bigger than in the plaintext domain. In MPC, the share domain has about the same size as the secret domain, so you don't have this. The problem is if you have lots of nonlinear computation, you need a lot of interaction with everybody. And you can't really optimize it, because sometimes you need to finish some part of the computation before you can start the next, because you have dependency in your values. So, this is just a huge conversation that can take a lot of time to do. Yeah, and so in essence, while FHE can require lots of computation, especially for this bootstrapping that kind of refreshes the noise in your ciphertext, MPC doesn't require so much computation, but it requires communication, a lot of communication. But in practice today, this is cheaper and more efficient, or the MPC requires kind of less communication than FHE requires computation. So in practice, MPC is faster than FHE. But at the same time, this could be a bit of an unfair comparison, because the applications that MPC are suitable for aren't always the same as the ones that FHE is suitable for. And so it's a bit hard to compare, because there are some applications that you cannot do without FHE, and you cannot do them with MPC. So in that sense, the speed of MPC for this application is infinite, because it doesn't actually solve your problem. Whereas the other way also exists. There are things that FHE cannot solve and MPC does solve, and in that case, FHE doesn't compete. But if you just say, okay, let's compute a complex function, MPC does it faster than FHE most of the time. The problem is you need multiple parties, because you trust them not to collude. But it's also, you can't just say, okay, I'm going to spin up like 10 Amazon AWS instances in the US, put one party on each of them, and then make them do the MPC. Because if you say, okay, there are 10 instances, that's good, but they're all controlled by Amazon, and they're all in the US. So that's kind of like, if Amazon decides to figure out what's going on, they can. They can open up their server and check what's happening in the share domain, and because they can see all 10 share domains, they can reconstruct. I'm not saying the US government would particularly want to hack Amazon, but if they did, they could also do that with Amazon knowing it, and then, so if this is your configuration where everything's happening under the same company or in the same location, you need to trust that this is secure. So typically what you'd want to do is you can put some of the instances in Amazon's cloud, others in Microsoft, others somewhere else, and then you say at least there's 3 different companies. And then you can say, I want some of them in the US, some of them in Europe, some of them in Asia, and then you can trust that there's no single jurisdiction that would try to tamper with your communication. But now you've got distances, and you've got interfacing between those services, so your communication speed probably goes down. Whereas if they were all in the same data center, it probably goes a lot faster because they don't need to go as far. So you've just slowed down your communication, which is what MPC requires large amounts of. So you need to balance efficiency against trust and security. But MPC is currently deployed nonetheless. But the thing is, you do need to find fits into the business model. Because, okay, even if you manage to kind of really separate who you're going to involve, sometimes if you've got different data holders, you need to convince them that they all have an incentive to kind of participate in this system. So that's a bit of the difficulty with MPC, is you can't just say, oh, I have an MPC library, I'm going to license it, or I'm going to spin up a cloud that does it for people so that they can sort of pay me to use my MPC service, because you actually want different people to be running the MPC. Whereas FHE, you can spin up, you know, you can say I have an FHE platform, encrypt your stuff to whoever you want to, I don't care, and you can use my platform to compute. It's efficient, you just pay me for the computing service, and that's it. Easy business model. Whereas for MPC, it's a lot harder. So in the current applications that we have, they tend to be very bespoke, and sort of companies, they go to sort of little cryptography companies or professors, and they say, hey, we want something for this application, and then that's built, but then you can't just take that everywhere else. It's a bit, it's still a bit of a problem. The other issue with MPC and FHE goes back to the same issue as federated learning. MPC and FHE protect the inputs from what's happening like during the computation, but then they just release the output. So if you can learn something about the input from the output, MPC and FHE don't actually prevent this. So this kind of adaptive attack we saw against federated learning, where you would craft clever queries to extract information from the data set, well, if your queries are responded in an FHE secured way or an MPC secured way, you're still getting the output for the input you requested. And so actually MPC and FHE also aren't one-shot solutions to privacy preserving computation. You may need differential privacy in there as well to ensure that you cannot extract information about the input data set. And then you need to ask, well, okay, so we need to add the noise, where should it be added, at which point, is it in the input, is it like provided separately into the computation engine, all these kinds of questions as well that arise. The other thing about a difference between MPC and FHE is that in FHE there is a single party doing the computation. So if they decide to do a different computation than the one you asked them to do, you don't know about this, because they'll just return to you an encrypted result, and they'll say, here is your complicated computation result, and maybe you paid them for like, I don't know, 1 billion operations, and then they decided that doing 1 million was 1,000 times cheaper for them, so they'll just do something else so that the output looks the same to you, and then they'll bill you for what you asked them to do and actually perform a lot less computation. And you have no way of telling, because you're not going to redo the computation yourself, because that's the whole point of outsourcing it in the first place. So there is this active attack on FHE. Can they just compute the wrong thing? In MPC, this isn't possible, because in MPC you're required to interact. And you need to interact for every nonlinear step in the computation. And the moment you can see that someone is trying to take the computation a different way than the algorithm you agreed to execute, you can just stop interacting. And if you stop interacting, they can't proceed without you. So it's also an attack vector, right? As an adversary, I can just decide to stop computing, and then I'm blocking the whole system. But at least people can tell that it's me doing this. And then I can be punished in legal and other ways. but at least also the privacy hasn't been breached. I've just decided to stop the computation from proceeding, but everything's still in the shared domain. Nothing was actually leaked. So with MPC, this can be detected. So there's different levels of detection. You can detect that someone is doing something wrong and abort. As an honest player, you say, there's something fishy going on. I don't know who to blame, but I'll stop anyway, just to make sure nothing bad happens. And this is what we call active security with abort. So usually if you want to deploy MPC, this is the level of security you ideally want to aim for. There are higher levels of security, such as active security with identifiable abort. So you can tell that something fishy is going on and you know who to blame for it. So then you can, outside of the protocol, you can take measures to punish them. And there's also active security with guaranteed output delivery, which is that if you can tell that something is fishy is going on, you can recover from it by assuming that not too many people are malicious, not too many people are misbehaving, and you can recover what the correct intermediary value should be and then continue from that. So essentially it means it's tamper resistant, but then for these protocols, they usually become much more expensive in terms of communication and computation because you need to have redundancy. The only way you can recover from error is with redundancy, and so if you're doing redundancy, it means you're repeating computation unnecessarily when nothing goes wrong. The other thing is that some active attack, they don't just can cause the wrong result, they can also lead to privacy breach. So if you have an insecurely crafted algorithm, what can happen is the adversary can introduce errors that are detectable if the input is of a certain value, and the error is not detectable if the input is of a different value. So if the error gets detected, the protocol crashes because the honest parties are saying we've detected an error, we'll stop. But you crafted the error such that this leaks information about the input as well. So there is also these considerations to like how you're crafting not only the MPC protocol that allows you to execute an algorithm, but also how you're actually coding the algorithm in the steps that it's going to take. So if we want to have the same level of security with FHE, there is yet another form of what we call privacy enhancing technology. And here we're moving a bit away from the input privacy, right? Here we're talking about computational integrity. We want to make sure that the computation was done correctly. And this is what's called verifiable computation. And it's also called zero-knowledge proofs, which I think you've heard about yesterday or something like that. But they essentially solve the problem that we want to make sure someone did something correctly. And it doesn't always require confidentiality. So when we're talking about verifiable computation, we just care that they took the correct steps. We know us as the data holder, we know the inputs that they're supposed to use, because it's our data. We know the algorithm they're supposed to do, because that's what we're requesting. We just want to make sure they do it correctly and they can't lie to us. And that's kind of the proof part of a zero-knowledge proof. And that's why it's also called verifiable computation. So the idea is that you have this function and data provider sends over the instructions, and then when the computing party finishes the result, they also come up with a proof that they can send back, and then the data holder can check this proof against the specification of the computation and the inputs, and then double check that everything went well. And if this person used, let's say, an algorithm G rather than F, it should be very hard or infeasible for them to produce a proof that is as if it was computed using F. So you can't lie on the proof part. Now, zero-knowledge proofs also have a dimension of input privacy. And this is where the zero knowledge comes from. And the idea is that if you're, in the case where the person providing the proof also have inputs they want to keep private, so let's say this is the parameters for a machine learning model, right? And then this person wants to use the model of the provider, but obviously the provider doesn't want just to give the model because that's their business competitive advantage. but they also want to provide an assurance to the user that they really use the right model. So they can sort of publish a digital hash, a secure hash of their model saying, I have a model that has this fingerprint, and I'm going to use it whenever you query data to me. So then they can provide a proof that they're using the model that has the right hash, but they need to protect their inputs, and their inputs can't be visible from within the proof, and this is where zero knowledge comes in. And it does provide input privacy to the party providing the proof. The key sort of requirement is that, especially in verifiable computation, verifying the proof should be much faster than generating it, and also then redoing the computation that it's proving. Right? If you spend as much computational effort checking that somebody did the computation right as it would have taken to do the computation, you might as well have done the computation yourself in the first place. So in the VC setting, this should be particularly much faster because that's the only reason why you're using zero-knowledge proofs. Using a proof. So this is what we call succinctness. So succinctness is the fact that you can generate a proof that is much shorter and much faster to verify than the kind of the data that was required to compute it. There's many ways to do this. There's many different schemes that propose how to do this. But there is this kind of idea that there is, I don't know if it's been formalized before, it's perhaps an interesting direction. There is this kind of like overall computational effort that needs to be spent in order to provably perform computation. And either this can be spread equally across the proving and the verifying party, so they both do the same amount of work. This doesn't make sense for verifiable computation, but in a zero-knowledge setting, this could make sense. Or if you want the verifier to do much less work to verify the computation, this usually has an upwards effect on the proving time. So you usually have like a logarithmic overhead, if not worse, on the computation. So for every step in the computation you want to prove, you have extra steps to actually produce the proof of those steps in a way that can be very expensive. So generating the proof is usually the hard bit. But that's there's been a lot of interest, research, and investment in those, specifically ZKP and verifiable computing in the blockchain space. And it's not because blockchains try to be the new best technology thing, but it's also because on the blockchain, resources are very constrained. So if you want to store data on the blockchain, that's going to cost you money. If you want the blockchain, which is essentially a distributed computer, to perform proof verification for you, so you can have you can say I did something right, you put the proof on the blockchain, and then the blockchain is a trusted computer that's going to verify this. So everybody can see that you didn't lie in the proof that you made, but you need to pay for every computational unit you're going to request for the blockchain to compute. So in the blockchain area, you really want short proofs and very fast to verify because that's going to be the cheapest solution for you. And in the last 5 years, this has driven a huge amount of performance into zero-knowledge proof systems to the point where there's now like Rust things you can just download on the internet and run on your laptop. And they're not very fast, but they're there. They exist. And this is miles ahead of where we were maybe just 5 years ago in this technology. So to summarize a little bit the different technology we've seen, we can kind of place them like this, where you've got kind of the security assumption or reasoning and the kind of privacy you're achieving for your computation. On the left, we have the more mathematical cryptographic ones, where you can usually say there is a computational assumption or there is an information theoretic argument as to why this is secure. MPC and FHE provide input privacy and input privacy only, so you can still recover things about the input based on the output. Proofs provide verifiable computation. Zero knowledge provides private and also a bit of input privacy, so ZK should technically be a bit higher. And then when you go to the more statistically secure, you have federated learning for the input privacy, and then you have differential privacy, which for the moment is the only thing we know to how to secure outputs. And then you've got hardware assumptions with trusted execution environments. I'll stop here. You'll see on the slides, there's a couple slides on like the state of the art of what the current challenges are and the bottlenecks for these different technologies. And then after that, there's a bunch of like application use cases, you know, different kinds of markets or auctions and things like this where technologies like this were used to give an idea. But I'll happily take a couple questions, and then I know you guys have coffee, so I don't want to get in your way for that.
Or face matching or face detection using on encrypted data? Is it possible, or?
I guess the theoretical answer would be depends how efficient and accurate you want it to be. So if you have a very basic model that does some form of basic facial recognition, it could be possible. If you want to have quite a large model that's very accurate, that might be stretching a bit the capacity. It really depends on like how deep the model is, how complex it is computationally. So I haven't heard of secure computation for facial recognition algorithms. My guess is it depends on how complex a model you want to execute. So it's probably fast enough. Probably not for like identification, right? If you want someone to like face ID on a phone, it probably won't be fast enough to be responsive enough for the user experience that you want. If you want to do like MPC analysis of footage and do facial recognition on that, and you can afford the time of the computation, then it's probably not horrible, but you just need to find the right coalition of MPC parties that would agree to kind of do this for the right reasons, whether that's money, legal, whatever. The challenge with MPC is not so much the performance of the computation. That might be an acceptable cost. It's more, can you actually get the people together to do it?
Okay, thanks again for a very interesting lecture. So now you deserved your coffee break, and we'll come back for a lecture on cybersecurity and AI at 11:30.